Alright, this is the first section of LNL's classical mechanics. Landau begins by introducing the idea of generalized coordinates in section 1. So one of the fundamental concepts in mechanics is that of a particle. And by particle, we mean any body whose dimensions may be neglected in describing its motion. For example, the planets can be regarded as particles considering their motion about the sun, but not in considering their rotation about their axes. And the position of a particle can be defined as a function of its Cartesian coordinates, x, y, and z. And we know from mechanics that the derivative of position is velocity, and this would just be the first derivative of our function. Same thing goes with acceleration. It's defined as the second derivative of our Cartesian coordinate function. Now, if we define the position of a system of n particles in space, it's necessary to specify n radius vectors. So if we're in three-dimensional space, we can move in x, y, and z. Thus, we can move in all three dimensions. And this would indicate that we have 3 degrees of freedom. Now, these degrees of freedom don't necessarily always have to be in Cartesian coordinates. They can be in cylindrical, spherical, whatever the problem makes more convenient. And if we redefine this idea as s quantities, we can call them Q1, Q2, Q3. So these would be our generalized coordinates. And if we define the velocities in the same way, q dot 1, q dot 2, q dot 3, this would be our generalized velocities. Now, if we just know the generalized coordinates, we can't really tell anything about a particle, because if it's here at one point and at another point it's here, but we don't know exactly its velocity, we cannot tell where it is at t3. But if we happen to know its position and its velocity, then we can predict its next position at the third interval. Now, the relation between accelerations, velocities, and coordinates are called the equations of motion. And they are a second order differential equations for the function q of t. And their integration makes possible, in principle, the determination of these functions and so the path of the system. So if the relation between q dot gives us the equations of motion, and if we integrate them, we can describe the path of the system.